All right, guys, we got quite a few questions, examples to get through today with the sum and difference formulas, which will culminate in a very, I think, difficult question that we come across throughout the course, but it parallels well with what we've already done previously. Okay, it's a question that throughout the course builds on itself. Okay, and we keep seeing this format of question. If I gave you the question, tangent of theta equals 3/4, and theta is in the first quadrant, can you tell me the other trig ratios? Okay, we've done that. Okay, today we're going to extend that question a little bit, dealing with now two angles, a sum of two angles. Okay, in order to get there, we need to revisit our sum and difference formulas. Okay, and as we go through these throughout the day, I understand you've only seen these sum and difference formulas once, and that was on Thursday, 3 days ago. Okay, I'm going to go back and forth between them, but if you don't know what they are as you're going through your homework, you can't remember them, you're going to have this in front of you. My suggestion to you strongly is to somehow develop a device that allows you to replicate those quickly, so you don't always have to reference your notes. Okay, but I want to deal with these a little bit today, because if you were to ask me right now, Mr. Fay, what is the sum and difference formula for tangent, I don't know it. And even after we come up with it, I'm not going to commit it to memory. Okay, I know how it's made, and you already know how it's made, so that's what I want to go through. I want you to see where this thing, because that's very dissimilar to these. Okay, we walked through on Thursday. I think we did the cosine, the proof of the cosine, try to show you a little bit of how then the sine formulas come from that. But these don't look like anything like these. Okay, so let's see if we can come up with these. And you already know it. Okay, it's just not something that is extremely visual right now for us. Okay, so if I ask you, what is the tangent of s plus t? Okay, the tangent of s plus t is the quotient, right this way, of sine of s plus t divided by cosine of s plus t, right? Remember what this is saying is if that's 75 degrees, the tangent of 75 is the same as sine of 75 divided by cosine of 75. And that's something we've known since day one of trig, right? Okay, tangent is the same as sine of cosine. Sine divided by cosine. Well, these things, okay, now it might seem weird the way I write this. It's because I know what the next step will be. I'm going to give myself a little bit of room here. So I'm not going to write what sine is right here. I'm actually going to write it on this line here. I'll give myself a little bit of room here because I'm going to come back and do division. And I just want room to do that division. Does that make sense? But sine of a sum is sine, and then it goes cosine, and then the same sine that is here, and then cosine, and then sine. This cosine here on the denominator, because it's cosine, goes cosine, 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 which I parallel to being the opposite of that, so that's positive, so cosine would be negative, and then sine, sine. And again, I'm going off memory of those. I developed a strategy that allows me to get those quickly. If you need to look at your notes, you need to look at a reference sheet, that's fine, okay? But obviously, committing those to memory in some fashion makes things a little bit easier. Now I need to put these arguments in. The arguments always go in order. ST, ST, then down here, ST, ST. And right now you have four, just going to highlight them, 4 products. Okay? You could go through and look at each one of these products. We want to divide these by something because we want tangent to show up. Okay, because this is tangent, so it'd be nice if the rule had tangent in it, right? Does that make sense? Okay, so we want tangent to show up, and we can go divide by this one, or we go divide by that one to every one of these 4 products, or we can do it with that one. The one that turns out to be the cleanest, most appropriate to divide everything by is this one. That's kind of why I left the room I did at the beginning. I want to go back through, and I want to divide this by cosine S, cosine T, divide that by cosine S, cosine T, cosine S, cosine T, and then this one, cosine S, cosine T. What do I get right here? Let's just start in this top one. What's sine S? Let's do this first. Why did it do that? What's that quotient right there? 1. And then what is sine S divided by cosine S? Tangent S. So we can make that substitution. That thing turns into tangent S. Okay. What is this here give me? What's cosine S divided by cosine S? 1. And then what is sine T divided by cosine T? Tangent T. So plus then tangent T. What's cosine S divided by cosine S? 1. What's cosine T, cosine T? 1. So 1 times, it doesn't disappear. It's a quotient of 1 there, right? Minus then, what's sine S, cosine S? Tangent S. And what is sine T divided by cosine T? Tangent T. And that then is the tangent of S plus T. Yes, Sam. Because I had 4 options. I could divide it by this one here, or that one, or that one, or that one. If I were to see all 4 iterations of division, this is the nicest one to do it. So just through kind of trial and error. And I don't want us to go through all those and realize and make the comparisons at the end, but that one ends up being the best. So then we can look at, this is a sum, but we can make the difference. I don't want to go through this, but we can make the difference that way. So then tangent of, so this one would be negative T, this one would be negative T as well. And if you remember, if I have tangent of negative T, that's the same thing as negative tangent of positive T. And what that will effectively do then, if I want subtraction, it just changes that sign to a minus and that sign to a plus. Because of the relationships that this becomes tangent of negative T, that's tangent of negative T, and they can both be rewritten that way. But that's how those formulas are constructed. Which means if I have, let's just do a specific example here. Now this is going to be a task that demonstrates why college algebra 2 come before trigonometry. Which I think there's obviously a lot of the algebra that we did here is one of those reasons why algebra comes before dealing with the trig. But let's say I want the tangent of 75 degrees. I think most of us would probably agree that maybe taking the tangent of 45 plus 30 would be equivalent to that, right? And in our formula, so 45 is going to be the S, and 30 is going to be the T. So then I go tangent of 45 plus then the tangent of 30, all divided then by 1 minus the tangent of 45 times the tangent of 30. Is that okay with everybody? Okay. So now help me out. What is the tangent of 45? Anybody remember that from memory? It's 1. Okay. Plus then tangent of 30. If I go sine divided by cosine at 30, I'm going to have 1/2 divided by radical 3 over 2. 1 over root 3. And if I rationalize that, I'm going to change it to root 3 over 3. So that's that numerator. The denominator becomes 1 minus 1 times root 3 over 3. Okay? Now, here's the algebra. We don't like it written that way. That's messy. And this becomes a much more concise, real nice answer when we're done with the algebra here. So I'm going to look at the grouping at the top, and I'm going to rewrite that as a common denominator. So the common denominator is going to be 3. So this will be 3 plus root 3 over 3. That's what that numerator turns into when I add those together. Okay. On the bottom, it's the same idea, but it turns into 3 minus root 3 over 3. Okay. Now, I got a fraction divided by a fraction, and when I multiply by the bottom reciprocal, or because these denominators are the same here and there, I'm left with 3 plus root 3 over 3 minus root 3, which is better looking than what we started with, right? But still not great. Anybody remember how to get rid of a radical like this in the bottom when it's not a product down there? It's a sum now. 3 plus, what's that called? Multiplied by the conjugate. So 3 plus root 3 over 3 plus root 3, so multiplied by 1, but in conjugate form. And the reason we do that, multiply by conjugates, O and I cancel out. So all I got to do is first times first is 9. Last times last gives me negative 3. Multiply on the top, those are not conjugates, so there you have to FOIL. So 9 minus 6 radical 3 plus 3. That gives me 12 minus 6 radical 3 over 6, right? I don't know why I made a negative there. My fault. Thank you. So 12 plus 6 radical 3 over 6, and that reduces, correct? 2 plus radical 3s. Why doesn't this 6 cancel with that 3 in the radical? Yes, that 3 in the radical is not, I guess the radical 3 is a symbol for approximately 1.7. And 1.7 and 6 do not have a common factor. Okay? So 2 plus radical 3, that is the tangent of 75. So if I go back to, we always want to check these, and I think it makes sense to use Desmos here. If I go tangent of 75, and I'm going to be in degrees here, I get that number right there. Okay? So if I told you, give me the exact value of tangent 75, and you turn to your calculator, it gives you 3.73205080757. You have no ability to change that back into what we call a surd, okay, which is an expression with a radical in it. Okay? There's no algebra to do that. But if we go through the process that we just went through, is 2 plus radical 3 the same thing? Yeah. So that's the purpose of these formulas, is because it gives us an exact value for these angles at 15 degrees and 75 degrees. Okay. Last class, what we did, we went through a procedure, because I think the next question on the notes is find cosine of 75. Okay. What I want you guys to see here is if I go cosine of 75, there's a lot of different ways that you can get 75. I like to deal with I like addition better than subtraction. So I like to deal with stuff in the first quadrant if I can. And if I can't use the first quadrant, I like to move it into the second quadrant because the angles are still smaller than what they would be in the third and fourth. Okay? But it should not matter as long as I can generate 75. So I like to take 30 plus 45. But your neighbor might say, well, cosine of 75, I can get that by taking 135 minus 60. You see that they're different, right? Okay. So let's go through and see if it changes anything. Okay. As long as this sum to 75, we should be okay. And that's what I want to demonstrate here. So it's cosine. So it goes cosine, cosine, cosine. So this is a plus, so this one's a minus. And then sine, sine. Then we're going to plug in my 30, my 45. 30, 45. And people always ask, well, does it matter if I went 30 plus 45 or 45 plus 30? Well, addition's commutative, and so is then multiplication. So no, it doesn't. Okay? Obviously down here it would. Okay, because if I go 16 minus 135, I don't get the 75 I'm looking for. I get the opposite sign. But now I go evaluate. What's the cosine of 30? Radical 3 over 2, right? Cosine of 45 is radical 2 over 2. Minus then the sine of 30, 1/2, and the sine of 45, radical 2 over 2. So when I multiply this together, that's going to give me radical 6 over 4. And this is going to give me radical 2 over 4. And that then is the cosine of 75 degrees. So on my unit circle, that is the x value when either t, the distance along the arc, is 5 pi over 12 radians, or if my central angle is 75 degrees. Okay, that's the x coordinate at 75 degrees. Now, I'm not going to ask you to memorize that because it's a very nasty number to memorize, especially when we look at the y value of that. Okay, because basically what happens is because of the way that we generate 75 and 30, or sorry, 75 and 15, is through the use of 30, 45, and 60s, okay, which is using the same radical 3 over 2, 1/2, and radical 2 over 2 values. When I go 75, look at the unit circle, trying to find the angle or the coordinates of the angles at 15 degrees and 75 degrees. They're always going to be radical 6s, radical 2s, and a denominator of 4. It's just that how these are combined will be different. Does that make sense? And it's really hard to keep them straight. Okay? So I'm not going to ask you to do that. If I need you to have the exact values, we should be able to run through this formula and get them. Okay? But if I go down here and use this approach, applying my formulas, cosine of 135, that's negative radical 2 over 2 now. Cosine of 60, that's the 1/2 now. Plus the sine of 135, well, that's radical 2 over 2. Sine of 60 is radical 3 over 2. Excuse me, negative radical 2 over 4, plus now radical 6 over 4. Is that the same thing as that? Yes. Commutative property tells me it is. Okay? So it doesn't matter what two angles you use to get your 75, as long as they get you 75. Okay? What that does on the unit circle, so let's go ahead and, well, let's go to the next one first, and then we'll see these things show up on the unit circle. So cosine of pi over 12, okay? My suggestion to you, I don't know where my unit circle went. Do not do these problems when things are in radians. There it is. Nope, can't get that one. So if I look at my unit circle, they want to know what cosine of pi over 12 is. Because I've got sixths, fourths, thirds, and halves, there's pi over 12 in here somewhere. It's just not obvious, right? Okay. In order to do that, what I would need to do is change all of these into 12ths and see which two I need to subtract or which two I need to add together to get 1/12. I don't like doing that. So what I do, if they want cosine of pi over 12, I'm going to take pi over 12 and change it to degrees. And it gives me 15 degrees. Multiply by my conversion factor, right? And now I do cosine of 15. And cosine of 15 is, okay, so we go 45 minus 30. Okay. Last class I wanted to do 60 minus 45. Will it work? Yep. Okay. So then I go, this will be cosine 45 times cosine 30 plus sine 45 sine 30. Okay. Cosine of 45? Radical 2 over 2, right? Cosine 30? Radical 3 over 2. Plus sine of 45, radical 2 over 2. Sine of 30, 1/2. So we get radical 6 plus radical 2 all over 4. That's the cosine of 15. Is that okay with everybody? Okay. Now I'm going to combine the last two questions that we just did. We said that the cosine of 75 was radical 6 minus radical 2 over 4. And we said the cosine of 15 is this. If the cosine of 15 is that, what is the sine of 75? It's the same as cosine 15 because they're complementary angles, right? So radical 6 plus radical 2 over 4. So on my unit circle right here at 75 or 5 pi over 12 radians, the ordered pair for that red point is now radical 6 minus radical 2 over 4, comma, radical 6 plus radical 2 over 4. Does that make sense? Those are the exact values for that position on our unit circle. Okay? But you can see, and again, you can realize that it'd be very easy to mess these up, right? Okay? And because subtraction exists, we'll see times where it's radical 2 minus radical 6. Okay? So it's just hard to remember them. If you want to, you can. But for the most part, those are the types of questions that they're going to ask us in our homework just to get used to using that formula. Okay? This is an alternative question. This is working backwards. They're going to give you the expanded side of things, and they want you to work back to the other side. So what format is this? Is this a sine or a cosine? It's a cosine. And because that's a subtraction sign, then it's going to be adding, right? I go 14 plus 46, and that gives me cosine of 60, which is 1/2. So that number right there is 1/2. Okay, it's if I give you 1/2, previously I could give it to you as like 2/4. Give it to you as 3 over 6. Okay, I can give it to you in different formats, right? here's a new format. Okay, I can give you 1/2 as 1 over radical 4. Okay, now I can give you 1/2 as cosine 14 cosine 46 minus sine 14 sine 46. Is that doable? All right. The next example is a proven identity example. Now, we've already proven cofunctions exist through transformations, okay? And when we did it with transformations, we then used even-odd properties to get them to show up like this. Okay, that was probably a week ago, maybe a little bit longer. Okay, now, now what they want us to do is prove this using some difference formulas. Okay, so what I'm going to start with here is the left-hand side. The left-hand side is cosine pi over 2 minus u, which that's a difference, right? So I'm going to rewrite that as cosine, complement sine, sine. That's the formula for cosine of an angle minus an angle. And then I'll plug in my s and my t. Pi over 2, and then u. Pi over 2, and then u. And when you do this, whenever I input an actual measurement inside a trig function, I can evaluate that. What's the cosine of pi over 2? What's the x value at an angle of pi over 2? 0. Now, cosine of u, I don't know u, so I can't evaluate that. What's the sine of pi over 2? 1. I can evaluate that. Now, I don't know u, so I can't evaluate sine of u. But what does that go to? 0. And this goes to sine of u, right? What's 0 plus sine of u? Sine of u. Is that my right-hand side? So we're done. Does that make sense? So it's an alternative way of proving what we already knew to be true from what we worked with transformations and even odd properties. All right, this is the culmination of today, and this is we've done this. If I've given you an example of like what cosine of let's just say theta was equal to, let's say, negative 3/4, and I told you that theta was in Q3, can you find sine of theta? We remember doing those? Basically what we do is, okay, negative 3/4, so it's got to be third quadrant, so I draw that. So cosine's got to be negative 3, that's got to be 4. Find that distance, and then answer questions about sine, right? We've done that. Now, we're going to extend it a little bit. Now I've got two angles that I'm subtracting, okay? So they want to know what value do we get for cosine of theta. Does anybody know what that symbol right there is? That is phi. Okay. They want to know what is the difference between theta and cosine of the difference between theta and phi. You can do this in one picture. I strongly urge you not to. Do it in two pictures. Draw a picture for theta, and then draw a picture for the angle phi, and label them. Okay? Because here's what's going to happen. They want us to figure out the cosine of theta minus phi. Well, that's a difference. So that's going to go cosine theta times cosine phi plus sine of theta times sine of phi, right? Do you know, so now we're looking at that expanded side, cosine theta, cosine phi, plus sine theta, sine phi. Do you know cosine theta? 8/17, right? So I can replace that with 8/17. Do I know cosine of phi? No. So that thing, cosine of phi, that I don't, I'm going to highlight it. I do not know that right there. Sine of theta. Do they tell me sine of theta? No, right? I don't know that. And for the same reason, I don't know sine of phi. Okay? So I only know one of those three things. But the picture should lead me to knowledge about those three things. Okay? A lot of examples you'll see, and this one's a little bit different because they give me a tangent of phi, but other examples you might end up knowing two of those. At most, you'll know two of those things down here. Okay? But the way we get these unknown values is to draw our picture. Those are the ones that we do not know. Okay? So we're going to draw a picture of theta. It says 8/17, but you're in quadrant 4. So I'll draw my picture, quadrant 4. 8/17, it's cosine. So 8 is that number right there, right? 17 is my hypotenuse. Do we have the ability to find that distance right there? Okay. So I'll call that, I'll just call my y value. I can say 17 squared minus 8 squared will equal y squared, right? 17 squared is 289. 8 squared is 64. Subtract those, you get 225. What's square root of 225? 15. Now, here's where it's important. You're in quadrant 4. That value, it is 15, but it's negative 15. Okay? Now, from that, you should be able to tell, because that's theta, you should be able to tell me sine of theta now, right? Is it sine of theta negative 15/17? And that will be one of those things that we substitute down in our formula. Okay? While I'm at it, I'm just going to go ahead and figure out what phi is. Phi, they say, or they express it in terms of tangent, and they tell me that we should be in quadrant 2. So quadrant 2. Okay, tangent is opposite over adjacent. So I need a fraction here. So my fraction is going to be a denominator of 1. Okay, so that'll be a 1. That'll be radical 15. Okay, now, which one of those is the negative? The 1. And now if I want to find this r value for my radius, r squared will equal negative 1 squared plus root 15 squared, which equals 16, right? So what's r going to be? R is going to be 4. Okay. Now, we have those two things set up. We should be able to make some substitutions. All right, cosine of theta. That was given, 8/17. Not only was it given, but you can come back up to the picture and confirm it. Cosine of phi. What's cosine of phi? Negative 1/4. That's a value that you did not know prior to drawing the picture, right? Plus then, sine of theta. So sine of theta, negative 15/17. And then sine of phi, all right, so when I multiply all that stuff out, I get negative 8 over 68. And this will be negative 15 radical 15 over 68. So I'm just going to put that all in one fraction. And that is the value of cosine of theta minus phi knowing that information about theta and knowing that information about phi. Now, a lot of work there, right? Be nice to check it, right? Okay. Now, they give me information here to actually tell me, because of the way we know how our inverse functions work. If they give me cosine of theta is 8/17, I should be able to use cosine inverse to find theta, right? So let's do this real quick. Let's take Desmos, and they tell me that, so I'll make sure I'm in the right mode. We'll be in degrees here. Okay, so we're good. They tell me that cosine theta is 8/17. So if I go cosine inverse of 8/17, that should be theta. Does that make sense? Okay. Now, just be careful, because is this a fourth quadrant angle? Is 61 degrees in the fourth quadrant? No. Okay. That 61 degrees, though, is the same as this angle right here where my cursor is. That's 61 degrees. So if I want a fourth quadrant angle, I'm going to take 360 minus that, and I'm going to call that t. That's theta. Does that make sense to everybody? If I, just to confirm this, I go cosine of t, I get that. Desmos is nice because it gives me this fraction bar. Same thing? Okay, so I've got the correct value for t. Okay, now they tell me the same thing for tangent of phi is negative root 15. So I'm going to go arc tangent of negative square root of 15, and I get that number. Okay, that's not a second quadrant angle, right? Negative 75 would be that angle there, right? Meaning, because of the vertical angle aspect, this angle here is 75. So how do I find phi? If this is 75, doesn't this phi have to be about 105? So the way I did that is 180 minus that. So in this case, because this is already negative, I'm going to go 180 plus that. And I'm going to call that P for phi. But I should be able to say now tangent of P gives me that number right there, which is the negative square root of 15, isn't it? Okay. So we've got T and P. So what I'm going to do then is see what T plus P, come on, looks like. That angle right there. So I guess I didn't want T plus P. I wanted to know, was it subtraction? T minus P? Theta minus phi. I did that last class too. I made that a plus, so it's minus. So I want to know, what is the cosine of that thing right there as an exact value? Okay. Well, cosine of T minus P is that number right there, correct? We just found as an exact value, negative 8 minus 15 square root of 15 all over 68. Is it the exact same number? Okay. So we can use, if we want to check to see if this number is correct, we can use our knowledge about the sine inverse, cosine inverse, tangent inverse to actually find T and P, to actually find theta and phi from the ratios that they gave us. And then ask Desmos to actually calculate cosine, sine of their difference or sum, whatever it's asking for, and see if that equates to the exact value that we found. Okay. That process is tedious to check it, mainly because we have to pay attention. I think the place people mess up with is that they forget what quadrants they're in. They ignore that. They ignore it when they start the problem. They ignore it when they check. And if I ignore them, neither of those things are going to be correct in the actual process nor the check. Okay. That's as far as we got in the last class, and we only got about 4 or 5 minutes here left anyways. These proofs, guys, these other examples, and we will do this one tomorrow. Okay. But example 5 and example 6, my hope is that you see that those are very similar to what we've already done. Okay. We did cosine of pi over 12, very similar to tangent of 17 pi over 12. All you got to do is change 17 pi over 12 to degrees, find two angles that add to that, and then apply your tangent formula. Okay. That proof down there, example 6, is exactly the same thing as what we saw here in example 3. Okay. We'll do this one tomorrow. And then we'll get into what we call double angle formulas, which double angle formulas are, if I have sine of s plus t, that means s and t are different, right? If I go sine of s plus s, that means s and s are the same thing, so I can rewrite that as sine of 2s. Does that make sense? Okay. So our double angle formula for sine, same thing for cosine, is generated using our sum and differences. Just now, it's solely sums and allowing s and t to be the same amount. So what we'll do with that is we'll be able to say, well, what is the sine of 60 just by knowing what the sine of 30 is. Okay. Or the sine and cosine of 30. So it allows me to know multiples by just knowing like a base value, a base ordered pair. So we'll do that tomorrow. Remember that the